Hello viewers, in today's session we are going to discuss a very important and conceptual problem related to Leibniz rule of differentiation under the integral sign, right? So in this class we'll solve this problem using the famous Leibniz rule, and here the problem is we have to find the intervals in which the function f of x which is given as x raised to 4 to x raised to 4 plus 1 e raised to minus t square dt is increasing or decreasing, right? So here with the help of Leibniz rule we have to find the intervals in which this function f of x, in which the limits are the functions of x, and the integrand is a function of only the variable t. We have to find the intervals in which this function f of x is increasing or decreasing, right? So let us first quickly see the statement of Leibniz rule for differentiation under the integral sign, and then we'll see how we can apply Leibniz rule to this function f of x to get the desired intervals, right? So now let us first quickly see the definition of increasing and decreasing function, right? Suppose we are given a function, say y is equal to f of x, right? Here we are not going into the detail, but we are discussing only the concept which we will use while solving this problem. So if we have a function y is equal to f of x which is continuous in some domain, then this function f of x is said to be an increasing function or strictly increasing function if the derivative, that is f prime of x, is greater than 0, right? For all x belonging to the to some interval, say I. And the function f of x is said to be a decreasing function if the derivative is less than 0 for all x belonging to some interval, say I2. Here we can take the interval I1, right? So for increasing function, the derivative or the slope must be positive, that is it should be greater than 0, right? For all x belonging to some interval, say I1. And in this case we have to find I1 and I2, right? And the function is said to be decreasing if the derivative is negative, that is the slope is negative, so f prime of x is less than 0 for all x belonging to the interval I2, right? So from here we can easily conclude that we are given here the function f of x, right? And we need to find out the derivative, that is f prime of x, in order to find out the intervals of increasing and decreasing, right? So let us find out the derivative. So now to get the derivative of this function f of x, we'll make use of the Leibniz rule. And the Leibniz rule says that if we have an integral in which the limits are some function of x, suppose the lower limit is u of x and the upper limit is v of x, and here we have the integrand as some function of t, then the derivative of this integral, that is d by dx of this integral, is given by f of v of x. That is, first we'll replace this t by v of x. V of x is the upper limit, u of x is the lower limit, right? So first we will replace this variable t by v of x, and then we'll find out the derivative of v of x, right? And then we have a negative sign, and then we'll replace this t by u of x. That is f of t is now f of u of x, and then we'll find the derivative of u of x, right? So here we are considering only the case when this function f of t is the function of t only, right? So here, this is the Leibniz rule for the differentiation under the integral sign. So now let us compare this integral with this one, right? So we have v of x is given by the function x raised to 4 plus 1, and u of x is given by x raised to 4, and the function f of t is given by e raised to minus t square, right? So now when we find out the derivative of this integral with respect to x, we have d by dx of f of x, that is d by dx of the integral x raised to 4, x raised to 4 plus 1 e raised to minus t square dt, right? So first we'll replace this t by x raised to 4 plus 1 due to this result, right? So we have e raised to minus x raised to 4 plus 1 square, and then we have the derivative of x raised to 4 plus 1, right? And then we have the negative sign, and then we'll replace this t by x raised to 4. So we have e raised to minus x raised to 4 square, and then we have the derivative of x raised to 4, right? So this is due to the Leibniz rule. So now the derivative d by dx of f of x is given by f prime of x, and we can now easily simplify this expression. So we have e raised to minus x raised to 4 plus 1 square, and then the derivative of x raised to 4 plus 1 is simply 4x cube, and then here we have e raised to minus x raised to 8, because 2 times 4 is 8, right? And the derivative of x raised to 4 is 4x cube. So now the derivative, that is f prime of x, can be written as we can take 4x cube common, so we have 4x cube, and then we have e raised to minus x raised to 4 plus 1 square minus e raised to minus x raised to 8. So viewers, we have obtained the derivative of this function f of x like this, and now we'll do some algebra to arrive at the desired interval in which the function is increasing or decreasing, right? So let us first consider this expression, that is x raised to 4 plus 1 whole square, right? So here we have x raised to 4 plus 1 whole square. So let us begin with this expression. Now this is of the form that is a plus b square, so we can simply apply this identity, and now we have a square. A square is x raised to 4 square, then we have 2 times x raised to 4 times 1 plus 1 square, so we have x raised to 8 plus 2x raised to 4 plus 1, right? So this is an important step in this problem. So x raised to 4 plus 1 whole square is equal to this trinomial, right? Okay, so now see here, if we see this term, right? See, x raised to 8 is always positive for all values of x, right? And similarly, 2x raised to 4 is again a positive term for all values of x, because here the powers are even and 1 is obviously positive, right? So this entire term is positive. So from this expression, we can easily conclude that x raised to 4 plus 1 square is always going to be greater than x raised to 8, because here we have the extra term, that is 2x4 plus 1, right? So this is an important step in this problem, right? So let us revise it. So x raised to 4 plus 1 whole square is equal to this expression, right? So x raised to 4 plus 1 square is always greater than this term x raised to 8, because this is the excess term, right? So this is the extra term, and this term is always going to be positive, 2x raised to 4 plus 1, right? So now we have this inequality. So now let us proceed from here. Now what we will do, will multiply both sides by minus 1, right? Because here we have minus x raised to 4 plus 1 square, and here we have minus x raised to 8. So multiplying both sides by minus 1 will get this inequality, that is minus x raised to 4 plus 1 square. And remember, the direction of the inequality get reversed, so we have minus x raised to 8, right? Okay, so now what we will do, will raise these two terms to the power of e, right? So raising both these terms to the power of e, will get e raised to minus x raised to 4 plus 1 square. And remember, the direction of the inequality doesn't change, it remains the same, because the exponential function is an increasing function, right? So here we have e raised to minus x raised to 8. So the direction of the inequality remains the same, because the exponential function e raised to theta is always an increasing function for all values of theta belonging to the set of real numbers, because the derivative of e raised to theta is e raised to theta, right? And e raised to theta is always greater than 0 for all values of theta belonging to the set of real numbers. So now transposing this term to this side, we have e raised to minus x raised to 4 plus 1 square minus e raised to minus x raised to 8 is less than 0, right? So this is an important inequality. So viewers, now let us denote this term, that is e raised to minus x raised to 4 plus 1 whole square minus e raised to minus x raised to 8 by say p, right? So we have p less than 0, right? So we can also write this inequality like this. So p is less than 0. So now let us consider this derivative, that is f prime of x can now be written as 4x cube. And here we have assumed this term as p, right? So here we write 4x cube times p. So now f prime of x is equal to 4x cube times p. So we have, we can also write it as 4 times x cube times p, right? Now this p is less than 0 from inequality 2, right? So this quantity is always going to be negative, because p is less than 0 for all values of x belonging to the set of real numbers. We have just proved that p is less than 0, right? So this is for sure that this p is always negative for all values of x belonging to r. So now the sign of f prime of x depends on this quantity, right? Because 4 is already positive and p is negative. So the sign of the overall sign of f prime of x, it depends on x cube, right? So now here two cases arise, right? So when x is greater than 0, it means x is positive, right? So when x is greater than 0 or x is positive, then x cube is obviously a positive quantity, right? So in that case, the sign of f prime of x is negative, because here 4 is positive, that is this is positive, then x cube is positive, and p is negative, right? So when we multiply these three signs together, then we'll get negative, right? So when x is a positive number, that is x is greater than 0, then f prime of x is negative. So it means f prime of x is less than 0, right? F prime of x is less than 0. So the function f of x is a decreasing function when x is greater than 0, right? So now consider the second case when x is negative, that is x is less than 0, so x is negative, and in that case x cube is also going to be negative because here the exponent is an odd number, right? So we have x cube negative. So in this case the overall sign of f prime of x is now 4 is already positive, and then we have x cube. X, the sign of x cube is negative, and p is already negative. So when we multiply all these three signs together, we'll get positive, right? So when x is less than 0, then f prime of x is greater than 0. It means it is positive, right? So in that case the function f of x is an increasing function, right? So viewers, this is how by making use of Leibniz rule, we see that when x is greater than 0, the function f of x is a decreasing function, and when x is less than 0, then the function f of x is an increasing function. So viewers, now we can write the intervals in which the function is strictly increasing and strictly decreasing. So when the value of x is greater than 0, it means when we have the interval that is 0 to infinity, then the function is strictly decreasing, right? And when x is less than 0, it means when we have the interval that is minus infinity to 0, then the function is strictly increasing, right? So these are the two required intervals.